Hi folks. Today's lesson is all about trig modeling and using that trig modeling to answer some questions. There's no real new concepts here. We already know how to get the equation from a graph. In this case, we'll just be also using those equations and putting them in context. So if you want to get the most out of this presentation, probably the best way to go about it would be just to pause on each question, try and run it through yourself, and if you get stuck, then unpause and check out what the solution might be. Alright, we'll jump in with Ben, who's a fisherman with a boat in the Rill Harbor. So we've got some Welsh representation here. This is part of the graph of the depth of the water at the mouth of the harbor. Find the amplitude of the function. So to find the amplitude of the function, what I like to do is I like to first find the midline. You don't have to do it this way, but that looks roughly like the midline. And we know some important points here. Here's the point 48, here's the point 10.2. And the midline, which is not what they're asking for, is always just max plus min over 2. Now, you don't have to do it this way. If you can immediately see what the amplitude is, or even what the midline is, then go for it. This is a technique that'll work every time. Oh my gosh, the midline is at 5. And that makes sense. That seems halfway in between. Once we know that, the amplitude's pretty easy to calculate. It's the distance between 8 and 5, or in other words, it's this vertical distance. Amplitude is 3. Find the period of the function. The easiest way to find the period of the function is to sketch a full cycle. And you want to choose values that are like hard to mess up. So if it were me, I would go from the top of the function to wherever it goes back to its max. And I'm asking myself, how wide is that? I started at an x value of 4, ended at 16. The period must be 12. It's 12 wide. We're going to model this as a cosine function. We could just skip to e here and we'll get all the stuff for c and d. We want to write down the equation of the function for the depth of the water in terms of m and h. So we want a cosine graph. We want something that's like a cos b x plus or minus c plus d. We'll use different letters. We actually already know what a is for the amplitude. And we know for part d what the vertical shift is. That's the midline, is 5. The b is going to be a little trickier. B is 2 pi over period. So 2 pi over 12, or pi over 6. And finally, we need the horizontal shift. The easiest way to do the horizontal shift is to find yourself a max right here and ask, what is the x value there? So it shifted 4 right. What does that mean as a final answer? Well, we're going to say m for the height in meters. I think it's really annoying that they chose h here for hours, I guess. 3 cos pi over 6 for b. X minus 4 because it shifted 4 to the right. And then plus 5. We've got a nice equation. I guess we should have used h for our independent variable, so I'll put that in there. H for hours. Calculate the depth of the water at 9:30 a.m. Let's do that right here. So we've got to put in an h, or hour, value here. And it's kind of nasty that they gave it to it as 9:30 a.m. That means 9.5 hours. So we'd have 9.5 minus 4 plus 5. I'm just subbing in. And this is not a rough expression to work out. I just have to go to my calculator. I'm going to have, I think I have too many brackets here. I wanted to close this bracket over here. There we go. And I can work through this stuff. Pi over 6, 9.5 minus 4 is 5.5. If you're careful, you can put it in your calculator exactly how it is here. If you're feeling a little paranoid about it, then maybe you'll do some simplification yourself. So this is 5.5 pi over 6 plus 5. Okay, now 5.5 pi is not a good final answer, but it's fine for getting your way to the final answer. Let's head to the GDC. I'll check that I'm in radian mode. Yep, looks good. And so I'm going to type in 3 cos, get my nice fraction by pressing alpha y equals 5.5 pi over 6, and then plus 5. I'll just hit enter. It tells me 2.10, and I go write it down. So that is the answer to part F, 2.10 meters. Let's see if it makes sense. At time is 9.5 right here. Yeah, the height is pretty low. It's really close to low tide. So it makes sense that we'd have 2.5 meters, or 2.10 meters rather. Ben's boat can only get in and out of the harbor when there's at least 4 meters of water at the mouth of the harbor. And Ben sleeps until 10 a.m. So when he wakes up, oh no, we're at low tide. He can't get out. When can he get out to fish next? So here they've told us that M, the M value, is 4 that we're interested in. So we're going to have this equation to solve. 3 equals cos pi over 6. H is unknown. Minus 4 plus 5. This is a pretty rough equation to solve analytically, but that's why we just go to the graph. I'm going to put in y equals 4 for one side. I'm going to put in 3 cos. I use my nice fraction button so that I can get pi over 6. I'm going to be really careful about my brackets here. I'm going to have m minus, h minus 4, so x minus 4, close, close, plus 5. Now I also have to think about my window settings. I don't need to see negative time, so I can just put in 0. I do need to see past 10 a.m., so maybe I want to see a full day. I want to see to 24 hours. I don't need to see negative y values, but I do need to see up to y values of at least 8 for the maximum height. So these seem like reasonable graph settings. And I graph, and there we go. So if I'm looking through this, here we are at 10 a.m. when he wakes up. Oh no, can't go yet. But somewhere around here, that's when he's first going to be able to get out again, when the value is at least 4. And how we find out where that is to go second, calc, intersect. Okay, and there are my 2 curves. Left bound, right bound. This is a little bit nicer on your calculator than mine. And it tells me that purple point, it's hard to see it there. It's purple. It says P1 is 12.35. So H is going to be 12.35 hours. Now, if we want to give that as a time, it's 12 o'clock and something. I have to figure out what's 0.35 hours in minutes. And this is where a little unit analysis might help. 0.35 hours times 60 minutes per 1 hour. And if you times 0.35 by 60, you're going to end up with 21. So it's 12 hours and 21 minutes. In other words, it's 12:21 p.m. So that first one had the graph given to us. In this one, we're going to have to generate the graph. Jensen's going on a Ferris wheel. The diameter of the wheel is 20 meters, and it makes 1 complete revolution every 30 seconds. When Jensen sits in his seat, his eyes are 1 meter above ground level. Okay, so here we go. Here's our Ferris wheel with a diameter of 20 meters. And also, he gets on, and he's 1 meter, eye level's 1 meter above the ground. Plot Jensen's eye level for the first 30 seconds. So obviously, it starts at 1 meter. This is going to be height. And we'll do time in seconds. 30 seconds later, since it completes a full revolution, he's going to be back at the bottom. Halfway in between, he's going to be at the top, wherever that is. And we can reason out that the top here is going to be 20 meters plus another 1 meter. So 21 meters. because the Ferris wheel doesn't start exactly at ground level. And I can start to make a little trig function for this. Because of course it's circular motion, so it's going to be triggy. I'll do my very best job here. I know this occurs at 15 seconds. I know it's 7.5 seconds and 22.5 seconds. It's going to be on the midline, which is right here. I'm going to draw it in. And the midline's halfway in between 21 and 1, so it's at 11 meters. There we go. We've got a graph now. Having the graph is what's going to help us write a trigonometric equation to model its height after t seconds. So when I look at this one, I see a flipped cosine. You don't have to see it that way. But if we do it as a flipped cosine, it has no shift at all. So I know that the midline is at 11. I know that the amplitude, we can figure that out, is going to be 10. Amp is 10. I know that the period is 30 seconds because it takes 30 seconds to do a full revolution. So B is going to be 2 pi over 30 or pi over 15. His height, if I do it as a flipped cosine, it's going to be negative 10 cosine pi over 15 t plus 11. Okay, no shift required on a negative cosine graph because it starts low. There are other possibilities, though, that you could choose. You could also have done it as a positive cosine graph. If that's the case, then you're interested in the x-coordinate of this max, which of course is 15. So it would be pi over 15, t minus 15 plus 11. If you wanted to do it as a sine graph, you certainly could. I don't know if that's the easiest thing, but it's not particularly difficult. So we'd have a shift in that case of 7.5 because we'd care about this kind of point. Okay? And we'd still have all of our other parameters being the same. So notice it's only the shift that changes depending on how you conceptualize it. Find his height after 10 seconds, so that just means subbing in some values. H is going to be, I'm going to use it from my basic function here, pi over 15 times 10. I like this version. Same thing for the next one. I just put in 75. And the last one I put in 120. Now, you might want to go to your GDC and make sure that you can do this properly. If you're having trouble, I really think what you should do is do a little bit of the simplification yourself. Do that pi over 15 times 10, so you get 10 pi over 15 plus 11. When you run this through, you should get answers of 16 here. You should get an answer of 21 here. You should get an answer of 1 here. Now, we can check against the graph, and it's probably worth doing. After 10 seconds, 10 seconds would be right about here. Yeah, 16 seems reasonable. Let's think about when he's at the top. He's at the top at 15 seconds, and then again 30 seconds later at 45, and then again at 75. So this one makes sense. And lastly, 120, well, he's at the bottom at 0 seconds, and at 30 seconds, and at 60 seconds, and at 90 seconds, and finally, he's going to be at the bottom at 120 seconds. And maybe he'll go around more and more. All right, suppose Jensen's afraid of heights and gets really freaked out when he's more than 15 meters above the ground. In the first revolution, over what time interval will he be terrified? Let's look at the graph here. 15 meters is like about here. Maybe I'll choose a different color for this. He's going to be terrified from here until here. If I had to estimate those times, I think they're about 10 and 20 seconds. So let's imagine his trip through this. He's going on the Ferris wheel. He's feeling okay, feeling okay, feeling okay, feeling okay. And then once we hit 15 meters, it's and then once we get down past 15 meters, he's okay again. So the question is, when does that start and end? they've told us in this case an h, or height, value. And I know in the first question h was for hours. I think that's real annoying. H for height makes more sense to me anyways. Okay, so we've got an equation. And you can use any of the three or some other ones of these models that you came up with. I'm just going to use the negative cosine one because I think it looks the easiest. I got to find out when that starts and when that ends. So heading over to my GDC. I'm going to put in y equals 15. I'm going to put in negative 10 cos. I put in that nice fraction, which is going to be pi over 15. And then I'm going to put an extra set of brackets here just in case. Close, close, and then plus 11. And now I think about my window settings. I care about the first 30 seconds. And x's are time here. So 30 seconds. I do need to see the full extent of the motion on the Ferris wheel. So it's got to go to at least 21 in height. Maybe I'll go to 25, not 1,025. And then I'll hit graph. And you can see that this is the point where he starts to be terrified. And so it's around 9.5 seconds. And he stops being terrified at around 20.5 seconds. I'm going to use intersections to answer these questions. So second calc, intersect. This is my left bound. That's going to be my right bound. And it says 9.46485. So we'll call that 9.46. This is the intersection that's in purple. We can also do the same thing for the next intersection. So intersection, the left bound is here. The right bound is here. And you'll have to guess, but I don't have to do that on this emulator. And it says the intersection's at 20.5. So the question was, over what time interval is he going to be terrified? From 9.46 seconds all the way up to 20.5 seconds. So for a good 11 seconds there, he's going to be terrified. And finally, we've got a question where you're given the equation. So we had one where you're given the graph, one where you had to generate the graph, and then the model. Here you've got the model or the equation. It should say the height of the tide is given by the equation. I'll clean this all up for the notes that are downloadable. 4.3 cos pi over 6t minus 4 plus 5.7. In this equation, h is the tide height and t is the time since midnight in hours. So if I just think about this graph, I mean, I know that it's got a midline at 5.7. And I know it's going to have a max at t equals 4. So this is going to be time right here. Okay, and this is height. So its max is just going to be 5.7 plus 4.3. And I'm just going to generate like the basic version of this graph to start with. So there it is at 10. It's also going to have a minimum at 5.7 minus 4.3. So that would put it at 1.4. Okay. So here's what the graph does. It goes up to a max there. And then we've got to figure out the period. Well, I guess we can answer question A without doing anything more. What's the maximum tide height? It's 10 meters. When does it occur? At t equals 4, or that means 4 a.m. Okay. What's the minimum tide height, and when does it should say first occur? So let's check that out. In this question, the period's going to be 2 pi over b, so 2 pi over 6, or 12. So this max is going to recur 12 hours later, or at 16 hours. Halfway in between those, at 10 hours, it's going to be at its minimum. So essentially the graph kind of looks like this for tide height, and it's also going to go back down here. So you're going to have a minimum of 1.4 meters, and that's going to occur at t equals 10 because of the period of this function. Our next question is, what's the tide height at 1:30 p.m.? So this is kind of sneaky. They're telling us 1:30 p.m. T is just hours since midnight. So at 1:30 p.m. you'd be 13.5 hours since midnight. And we just need to sub that into our equation. 4.3 cos of pi over 6 t, which is 13.5, minus 4, plus 5.7. And if we throw that into our calculator, you can pause and check it out. But it's going to give us 6.81 meters. And that seems reasonable. Let's think about that. 13.5 hours would be around here. It's going to be a little above 5.7 meters. Yeah, maybe you have 6.81 meters. Now, if you hear stuff in the background, that is just my pooch playing with his bone. All right, the next question is, in the first 16 hours, list all the times that the height's at 5 meters. So let's think about that just graphically before we head to the GDC. If I were to figure out when all the times are when it's at 5 meters, I mean, maybe here. I'm not sure if there really is one to start with there or just after 0, but I guess we'll find out on the GDC. And so essentially we need to solve the equation 5 equals 4.3 cos of pi over 6 t minus 4 plus 5.7. Let's head to the GDC and solve that. So I've put in y equals 5 for one of the equations and then the actual function for the other one. I need to make sure that I am in radian mode. Oh no, I'm not. So go over here, radian. Then I got to think about window settings. I know I'm going to want to go from 0 all the way up to 16 in my x's because it asks about the first 16 hours. My y's, I could go from 0 up to 10, I guess. I'm going to go up to 15 just to be safe. Sorry, 0 to 15. So that I get a nice view of the graph. And if I don't get a nice view of the graph, then maybe I'll change my window settings. Okay, and so now we have our graph and we can find those points of intersection. We can estimate them here, and here, and here. Or I could use the intersection and actually find their values. So left bound, right bound. One of them's going to be at 0.6877. And you're going to find other ones using the same technique at 7.312 and 12.687. So I'll just write those down, but you could find them, and we can see good estimates of them here. You can see that x value is about 7.3, and it's 12.7-ish. So there are 3 t values. They're not really times of day, though. If we wanted to find the time of day, I'd have to take 0.688 hours and times it by 60 minutes per hour. And that'll give me 41 minutes. That's what 0.688 hours is. So as a time, that is just 12:41 a.m. And similarly here, I'll have to take the decimal of the hour, the 0.312, and times it by 60 minutes per hour. And I'll find out that that's about 19 minutes to the nearest minute. So I guess this time is 7:19 a.m. Now, the last one. I could do the same thing, but I actually already know where it is. This first time is going to be at 12:41 a.m. This last time is going to be 12 hours later. So 12 hours after 12:41 a.m. is 12:41 p.m. That brings us to the end of doing some of these modeling questions. There are good ones in the book, though. So if you take a look at page 532 to 3, numbers 2 to 7, you'll find some good stuff there. I hope this has been helpful. Good luck with the material, folks, and take care.